Hello everybody, my name is Will. I'm a postdoc at Carleton University in Ottawa, Canada. Today I'm going to be presenting microtextural data of critical zone anorthosites in the western lobe of the Bushveld complex. I'm going to describe some petrological peculiarities of the Marinsky Reef, the boulder bed and the mottled anorthosites and suggest that these units may somehow be connected. This map shows the 5 zones of the Rustenburg layered sequence in the western lobe, and we have acquired and analysed samples from the annotated locations. The famous Marinsky Reef occurs in the upper portion of the critical zone, and this is also where we've sampled the boulder bed and the mottled anorthosites. In stratigraphic section, this is what the Rustenburg layered sequence looks like, and the upper portion of the critical zone is located here. To the right is our sample of the Marinsky Reef, and you should familiarise yourselves with the rock units. So at the base we have the footwall norite, the footwall anorthosite, the lower chromatite, the central pyroxenite, which in some cases is pegmatoidal, the upper chromatite, and the hanging wall pyroxenite. While the Marinsky Reef gets a lot of attention, there's also some unusual units underlying it, namely the so-called boulder bed and mottled anorthosites. So the boulder bed is a unit of anorthosites that contains centimetre to decimetre scale noritic to pyroxenitic boulders, and this is a lovely image showing some boulder-like features provided by David Reed. I'll describe some more petrological features of this unit shortly, but what is interesting is that this unit is enriched in all of the PGE relative to its bracketing units, but less so in base metals and sulfur. The mottled anorthosites are upper critical zone anorthosites that are pitted by these olivine orthopyroxene oikocrysts. Now there's no associated PGE enrichment with this unit, but there's still some interesting petrological features that I'm going to describe. So right now we're looking at element maps at the base of the Marinsky Reef at Rustenburg. To orientate yourself, the central map is going to show silicates and chromites as we pan upwards, and the map to the right is going to show accessory phases, primarily sulfides and phlogopite. So right now we're looking at the footwall norite. We can see these dark blue orthopyroxene oikocrysts that are partially to completely rimmed by clinopyroxene. There's very little quartz and sulfides throughout the footwall norite, and the abundance of sulfides increases as we reach the norite anorthosite transition. Traversing the anorthosite, we see what I call these sulfide highways that meander through the anorthosite and pool on top of the norite contact. This also coincides with an increase in the abundance of intercumulus orthopyroxene, which is also speckled through this sort of sulfide network as well. If we take plagioclase compositions of those adjacent to this intercumulus material, we can see that it is strongly reverse zones compared with plagioclase that is not adjacent to intercumulus material. As we continue to pan up, take note of this meandering sulfide network. We eventually hit an area rich in intercumulus clinopyroxene and then a zone of almost pure plagioclase directly underneath the lower chromatite. Now, plagioclase in this band is also strongly reverse zoned. And there are a number of textures I could elaborate on in the lower chromatite, but it would take me a very long time. So just for now, I want you to note this very sharp contact with some vermiform chromites and the undulose contact between the upper chromatite and the central pyroxenite. Sulfides and phlogopites and even rutile are sort of scattered throughout the lower chromatite. As we continue to pan upwards, we go into the coarse-grained central pyroxenite, which also has very coarse-grained sulfides compared with the other units. And then we hit the upper chromatite. Now, you may notice that the upper chromatite is far more discontinuous and compact than the lower chromatite, but it is also partially lined by phlogopite on both its lower and upper margins, and it also contains traces of chalcopyrite, pentlandite and phlogopite within it, but very little pyrrhotite. Directly above the upper chromatite, we can see we have medium-grained sulfides within the hanging wall pyroxenite, which show nice, well-defined pentlandite loop textures together with some phlogopite and quartz. This also coincides with the occurrence of clinopyroxene grains. As we pan upwards through that hanging wall pyroxenite, sulfides persist for a few centimetres together with quartz and phlogopite, and they eventually drop out a few centimetres above the upper chromatite. So as an update I gave from the presentation recently at the SGA, we tested the hypothesis that plagioclase grains in direct contact with intercumulus material were reverse zoned, and those not in contact with intercumulus silicates or sulfides were normally zoned. And unfortunately, as always, it isn't quite that simple. From a selection of high-resolution maps, while we see that normal zoning is more common in the leuconorite, zoning throughout the anorthosite, and particularly at the contact between the norite and anorthosites, is really rather complex. And to disentangle any spatial and chemical relationships there, we firstly need more samples. We'd need to characterize those samples in 3D to get a full feel for the spatial relationships, and then couple that with EPMA or LA-ICP-MS analysis to fully gauge the chemistry of those grains. It's an interesting observation, and more work needs to be done to bring some systematic observations out of the chaos we see here. So some more on the sulfides, and I've been skeptical to share some of these observations previously because I'm not sure that I fully understand them myself. But this conference seems like a great chance to share those observations without, without feeling obliged to explain them. So on the left is our map of the lower chromatite. We can see that sulfide highway there in the footwall anorthosite, and we can see sulfides and phlogopites speckled throughout. And interestingly, as I flick on and off the contact between plagioclase and orthopyroxene oikocrysts in the chromite, you may notice that these phases, together with rutile and apatites, seem to concentrate at their oikocrystic boundary. And the dominant sulfide in this case is pentlandite and chalcopyrite. Pyrrhotite does occur here, but most often pyrrhotite occurs as these decoupled interchromite masses together with very, very small proportions of pentlandite and phlogopite. And this is how they look in reflected light photomicrographs. Whereas chalcopyrite and pentlandite appear to be disseminated along this boundary, but they also occur as these blebby sulfides together with phlogopites entombed in chromite grains, and this is how they look here. And then if I take you 50 or so meters below the Marinsky Reef into the boulder bed, from many samples we see that although volumetrically quite small, the dominant sulfide at the base of boulders is pyrrhotite with very small amounts of pentlandite and virtually no chalcopyrite. So this time we're going to be looking at a pyroxenitic boulder in anorthosite, and we're going to pan upwards through that boulder. So firstly, looking at the base, we can see the occurrence of coarse-grained anhedral olivine together with coarse-grained orthopyroxene, and we're also seeing occurrences of chromite as well as sulfides, which are primarily pyrrhotite. Directly underlying the boulders, we have what's known as the marginal zone in this white dashed line here, and then underneath that we have the host anorthosite. If we measure plagioclase from that marginal zone, we can see that they're far more strongly reverse zoned than plagioclase of the host anorthosite. So now to pan upwards through the boulder, I want you to note the disappearance of olivine, chromite and sulfides, the overall decrease in grain size through the boulder, and the appearance of clinopyroxene as well as some phlogopite and apatites in the boulder as well. Then we eventually get to the top of the boulders and we start to see chromite occur at the top. And it's generally far less chromite, and it's not always present at the tops of boulders, but in some cases you can certainly see chromites lining sort of quite a large proportion of the boulders and even extending into the sides and walls of the boulders. To evaluate microstructures, we performed electron backscatter diffraction analyses of the Marinsky footwall anorthosite and the boulder bases. Particularly in the boulders, we thought we might see evidence for deformation if the boulders formed through fragmentation of a pre-existing layer. In our EBSD maps, we saw evidence for a weak fabric in the anorthosites, where plagioclase was oriented parallel to the rock layering, yet there was no discernible fabric in the boulder margin, and there was also no systematic size or shape variation in the grains. Now, these maps in the middle are maps of misorientation to mean grain orientation in cumulus plagioclase. These maps highlight internal grain deformation by plotting the relative differences in lattice orientation with respect to the grain's mean orientation. So in essence, they're highlighting changes in orientation across the individual grain. In these maps, yellow means relatively undeformed and purple means relatively deformed. Now, our maps show mostly yellow in both of these examples, with minor and localized grain misorientation. These are inconsistent with fabrics expected from plastic or mechanical deformation, and therefore we have no compelling evidence for systematic deformation. Furthermore, in petrographic analysis of these units, we saw no evidence for kinked grains or undulose extinction that might be expected. So now we get to the mottled anorthosites. I'm going to show an element map from this box here that samples at mottle from the Impala mine. In this map, we see dark purple plagioclase pitted by light green olivine that is rimmed by dark green oikocristic orthopyroxene. The mottle itself is surrounded by a halo of light purple that represents more anorthitic plagioclase, reminiscent of boulder bases. At the outer margin of this halo, we see an increased abundance of phlogopite as well as minor amphibole, and at the base here we may even see a fluid or melt pathway. In these enhanced element maps, we can clearly see the intensity of reverse-zoned plagioclase decreasing with distance from the mottle, and we can also see this abundance of oriented phlogopite lining the outer margin of this halo. So to bring this study together a little bit, how might these sorts of features have formed? With regards to the Mariinsky Reef and boulder bed, we must account for the underformed and strongly reverse-zoned plagioclase, the upper and lower chromatites, the coarse-grained pyroxenites, and the level of PGE enrichment. Now I'm going to focus on the boulder bed here, where despite only a number of studies, about as many mechanisms have been proposed for its formation. Firstly is one that isn't shown here schematically, and that's one of in situ crystallization, whereby we've had the accumulation of liquid within an anorthosite mat. Now, such models can't really account for the level of PGE enrichment we see, or the unevolved mineral compositions of the boulders. Secondly are models of ex situ fragmentation, whereby we've had the breakup or intrusion of a PGE-rich pyroxenite layer that was subsequently reworked to form the boulders. Now, without a stage of recrystallization in the presence of heat and or volatiles, such a model can't really account for the reverse-zoned plagioclase, absence of deformation, or the presence of chromatite. And it doesn't really explain the right way up nature of the boulders that we always see. Lastly are models of fluxed recrystallization of a pre-existing norite unit. Now we find that this model holds up for some of the observations we've made, whereby a pre-existing norite was reheated and or fluxed by volatile rich melts, causing it to melt and recrystallize. And this model can account for the level of PGE enrichment and also the petrological features we've described in this presentation. So in conclusion, I've hopefully shown you that despite differences in scale and level of PGE enrichment, the Mariinsky Reef, boulder bed and mottled anorthosites all share some similar features. This includes their coarser grain size, the presence of relatively undeformed anorthosite with strongly reverse-zoned plagioclase, and then with regards to the boulders and reefs, both have upper and lower occurrences of chromite, they have sulfides, they have PGE enrichment, and they also have things like similar mineral and whole rock compositions that haven't been presented here today. So our final takeaway message is that when working on any one of these marvellous units, the bigger picture must be considered, and the conclusions may have far-reaching implications for each of these units and not just the economically important ones. Thank you for listening. Here are some QR codes to some recent publications discussing these units, and I will now take any questions.